Hello, and welcome back to Physics 141 Classical Electromagnetism 1. We are now on the last topic for this chapter. But before we proceed, let's first review some of the concepts that we have learned so far. So, in the first chapter, we defined how to find the electric potential due to a given a charge distribution density rho. So we can actually just use Coulomb's law for the potential to solve for the potential at any point r. So in this lesson, we will try to expand that Coulomb's law for potential in terms of poles. So we have the monopole, the dipole, the quadrupole, the octupole, and so on. So let's now start the lesson. So how do you approximate the potential at very large distances? For example, you are given a charge distribution here, rho, and a volume tau. So if you want to find the potential at point r, v of r, then you need the location of the point r with respect to some origin, the location of your source charges within the volume, r prime, and the separation distance, curly r. Now, when r, the distance or the location of your field point, is very, very large as compared to the location or the distance to the source points, then your separation distance will just be approximately the location or the distance of your field point in this case. And if you have an electric monopole, for instance, a point charge, the potential of that will just be equal to 1 over 4 pi epsilon naught q over the separation distance is just now equal to r. So in your basic electromagnetism, you actually encounter this type of equation, and the assumption of that is that r is very much larger than your r prime, or it's very much farther from the, relatively farther from the point charge. So how about now if you have a dipole such as this, a pair of positive and negative charges separated by a distance d. So you may have encountered the term electric dipole moment before, which is just the magnitude of the charge of the two dipoles times the distance of the two dipoles, and this is always directed from the negative charge towards the positive charge. So what is the potential at distances far, very far from an electric dipole? So say we set our coordinates here. This is our x-axis, this is our z-axis. So again, we need to get the r prime, the source distances. So r plus prime is the distance vector towards the positive charge, r minus prime is towards the negative charge, r is our distance towards our field point, and this will be our separation distances. R curly r plus, separation distance from our positive charge to our field point, r curly r minus, our separation distance from the negative charge to our field point located at r. So you will notice that the potential is just due to 2 point charges, kq over r, kq over r plus, k plus kq over r minus. And in this case, we can simplify it to this. Okay, so when r now is very much larger than your r prime, which in this case is related to d, so we can have an approximation of this term here. But first, what is the curly r, the separation distance vector? So we use cosine law. So if this is theta, then these are your separation distance, r plus and minus. So the upper sign corresponds to r plus, the lower sign corresponds to the minus, the separation distance from the negative charge to our field point located at r. So since in our equation we need 1 over curly r, so 1 over curly r is just the inverse of this, so to the power of negative 1/2. So we do a binomial expansion in the approximation that r is very much greater than the separation distance of the two charges. So doing so will give us the approximation of 1 over curly r, or 1 over the separation distance vectors, as this one. So using this result, plugging it to this equation here, and we can approximate the potential of a dipole at very large distances. So it's just 1 over 4 pi epsilon naught qd cosine theta over r squared. So this is the potential of dipole for large r. So since qd, we defined qd earlier, q times d as just our dipole moment. So qd multiplied by cosine theta, that will imply some kind of dot product, essentially a dot product with a unit vector. So basically this is just the dipole moment component or the dipole moment component on the r axis. So you can I'm just gonna review some of your dot products here. So if you have, say, P, you will dot this with r hat, for instance. So according to the law of dot product, it's the magnitude of P, which is in this case is QD, times the magnitude of r hat. This is a unit vector, so its magnitude is 1, times cosine the angle between them. So QD cosine theta. So basically this QD cosine theta here is the component on r. So if this is your P, the dipole moment vector, and this is your r hat direction, then P dot r is actually this one, the component. This is P dot r hat. That's the component in the of P in the direction of r hat. That's actually the definition of dot product. It's the component of the first vector on the second vector. So in general, if you will recall, if you have a dot b, this is vector a, this is vector b, then a dot b is actually the component of a on b, so that's a dot b. Or you can also do the reverse, the component of b on a, that's still a dot b. So also dot product is commutative, meaning a dot b is equal to b dot a. So this is the basically P dot r, the component of P on the r hat axis. Maybe I think I should expound on that more, because we'll encounter more of that later. So for instance, you have a vector a, and say in Cartesian coordinates it has an x component, x hat, plus a y component, y hat, plus a z component, k hat. Okay, so for instance, we take the dot product of vector a and x hat. So this is our vector a, you dot that with x hat, and only one term will actually survive. It's ax x hat dot with x hat. That's the only term will survive. Ayy hat dot with x hat, that's 0. azk hat, sorry, it should be z hat. azz hat dot with x hat is also 0, and x hat dot x hat is equal to 1, so ax. So basically, if you have a vector and you dot it with a unit vector, you actually get its component. So if you dot it with the x unit vector, you get the x component, and if you dot the vector with the y hat unit vector, you will get the y component. So that's what I mean here. So since you dot P here with r hat, so this is the dipole moment component along the r hat axis. So something like P sub r, P dot r. Okay. So if we compare this electric potential for a monopole, you will notice that a monopole has a 1 over r dependence, and a dipole has a 1 over r squared dependence. So in terms of the monopole, Q here, we can actually think of Q here as the monopole moment, but essentially this is just the total charge. So we now generalize this to the multipole expansion. So a monopole is just a single charge. Its potential is dependent on 1 over r. A dipole are a pair of positive and negative charges, and its potential will depend on 1 over r squared. For a quadrupole, this is a quadrupole, its dependence will be on 1 over r cubed. For an octupole, it's 1 over r to the 4th, and so on. I don't know what a so this is 1, 2, 4, 8. The next in the series will be 16. I don't know what's a 16 pole is called, but we'll just stop here in the octupole. Actually, most of our calculations will just up to the quadrupole term. So in the monopole, you will notice that obviously there's a charge here. So the total charge is not equal to 0. And for the dipole, the total charge is 0. For the quadrupole and the octupoles, they're all 0. So the higher order terms actually have a total charge of 0. So starting with our potential, Coulomb's law for potential, we can actually use binomial expansion using the condition that r, the field point distance, is very much greater than the source point distances, r prime. And in doing so, we can expand this in terms of Legendre polynomials. So this is now our multipole expansion. So let's try to expand this summation. So the first term here is when n is equal to 0. So when n is equal to 0, you have r to the 0 plus 1. So now you have 1 over r. So r prime to the 0 is just 1. P0. P0 is the first Legendre polynomial, P0. That's actually also equal to 1. So basically, this is just integral of rho d tau. And so that's the first term, that's the second term, the third term. So the first term will actually be corresponding to the monopole term. So in the event that the total charge of your given system is not equal to 0, then the monopole term is the dominant term. So you can just approximate your potential up to the monopole term. So the monopole term is this one. So you will notice it's just kq over r. So integral of rho d tau, this is just our q, our total charge q. So the second term is the dipole. So that is when n is equal to 1. So when n is equal to 1, so you have r to the 1 plus 1, so r squared. So this is just r. P1 of cosine theta is cosine theta. So you have r cosine theta here. So this is now the dipole term. So in the event that the total charge of your given system is 0, then there will be no monopole term, and the dipole is the dominant term if the total charge is equal to 0. So this is the dipole moment component again. This integral here, this one here, or this one here, is the dipole moment component along the r hat axis. So the monopole is 1 over r, the dipole is 1 over r squared. Now, the third term is the quadrupole. So you have n is equal to 2. So when n is equal to 2, you have 1 over r cubed here. This is r squared, and this is P2. P2 is just this Legendre polynomial. P2 of cosine theta is 3 halves cosine squared theta minus 1 half, or 3 cosine squared theta minus 1 divided by 2. So that one. So that's the quadrupole term. So you can think of this integrand here as something like pertaining to the quadrupole moment of your quadrupole. So in doing or in using multipole expansion to solve for the potential, please don't use this very long equation. So take note, this is still plus dot dot dot. So depending on your expansion. So if you want to use multipole expansion as a solution to finding the potential of a system, you must solve each of the terms. You start with the monopole, the dipole, then the quadrupole. So you don't use this whole expanded equation here, because that will be tedious. That will be very, very long. Okay, so let's have an example. So here we have a sphere with varying volume charge density inside the sphere. So actually its volume charge density depends on r prime and theta prime. So we are now, take note, I'm just gonna go back. Take note that we need to write our coordinates inside the integral here in terms of r prime, because this r prime, this r is different from this r. This is the field point distance. This is the source point distance. So take note, r and r prime are different. So in this example, our charge density is in terms of the source coordinates. So because this is our source of charges, our sphere of charge with varying charge density. So it depends on r prime and theta prime. Okay, so we are asked to find the potential for points on the z-axis very far from the sphere. Okay, so we will use multipole expansion to solve this problem. Actually, you can use a different technique, but for this example, since this is multipole expansion, we will use the technique called multipole expansion. So we first start with the monopole na term. So KQ over R. So this is just the total charge na integral. Our differential volume here, d tau prime, will just be r squared sine theta dr dt d phi. The the differential volume in spherical coordinates. So obviously, in order to evaluate the monopole term, we just need to evaluate this integral, which is just a total charge. So plugging in our values of rho and d tau, so this is a volume integral. This is an integral with respect to r, theta, and phi. So for r, you will notice in the rho, there's an r squared here, r prime squared, and in the differential volume, there's an r prime squared in the numerator. So these two will cancel each other out. So for the r integral, you will just be left with kr r minus 2r, kr r minus 2r dr, and you evaluate that from 0 to capital R at the from the center of the sphere to the surface of the sphere. Now, for the sine theta, for the theta integral, you have a sine theta in the rho. You also have a sine theta in the differential volume. So therefore, you will have sine squared theta d theta in your sine theta integral. You evaluate again that from the poles, from 0 to pi, north pole to the south pole. And then for the phi component, there's no phi dependence on rho. And there's just d phi in the differential volume, so integral from 0 to 2 pi of d phi prime. So obviously, that integral is just 2 pi. And for the r, this is actually just a very easy integral. You will actually get kr cubed minus kr cubed here, and you will get 0. So since this is already 0, this makes the whole integral 0. So you don't, please don't. It's no longer required for you to solve this integral, because this integral is now 0. So therefore, the total charge is 0, and this means that the monopole term in the potential expansion is 0. So there is no monopole term when the total charge is 0. Okay, let's now go to the dipole term. So this is the dipole term in the multipole expansion. So obviously, we need just to solve this integral, which is just the component of the dipole along the r hat direction. Okay, so it's just the same integrals actually, but we now have an r prime here, and we now have a cosine theta prime here. So our integral will look like this. So it's just similar to this integral, but there's now an r prime here. It's just similar to this integral, but there's now a cosine theta here. So again, obviously that is 2 pi. This theta integral is actually just very easy to solve. You just let u is equal to sine theta. So therefore du, derivative of sine, is cosine theta d theta. So this will be u squared du. So integral of u squared du is just u cubed over 3. Evaluate that from 0 to pi. And since your u is sine theta, the evaluation of sine theta from 0 to pi is actually 0. So you will get 0. So you don't need to evaluate this integral anymore. So 0. So there is no dipole term either. So the monopole and dipole terms are all 0. Therefore, our only chance now is the quadrupole, because I really don't want to go to the octupole term. So I hope the quadrupole is non-zero. So let's now go to the quadrupole term. So obviously we need to solve for this integral first before we can evaluate the potential of the quadrupole. So our r will now have an r squared due to the r squared term here. Our theta integral will now have this corresponding term here, 3/2 cosine squared theta minus 1/2 d theta prime. And of course our phi is still d phi. So obviously that is again 2 pi. Now the r integral is just very easy, because this is just powers of r. So this is actually composed of 2 integrals. The first integral will be only r prime squared dr. The second integral will contain a term r prime cubed dr. So r squared dr, integral of r squared dr, and integral of r cubed dr. So that's just easy to solve. So solving that will give you a value of this integral will have a value of negative k r to the 5 over 6. Now this one is not so obvious. So in order to solve this integral, this theta integral, we need to recall the different identities for sine. Okay. First, you will notice that if you simplify this integral, you will actually get, can I write here? So you will actually get 2 integrals. So the first integral will be, there's a factor 3/2 from 0 to pi, and then you have sine squared theta prime cosine squared theta prime d theta prime, and the second integral will have a factor of 1/2 integral from 0 to pi, and then sine squared theta prime d theta prime. So this is now the expanded version of our theta prime integral. Okay, how do you solve this? So we need to use some identities. So first things first, the identity of sine 2 theta, that's actually 2 sine theta cosine theta. So you have sine theta cosine theta here, so actually you can convert that into sine to theta, and there's a squared, so sine squared to theta. And if you have a sine squared theta, that's actually just 1 minus cosine 2 theta over 2. So you will reduce your integrand here into functions of cosine theta. So you have integral of cosine theta, which is just the answer of integral of cosine theta d theta is sine theta. So you use this relation to simplify this integral here, and you will get an answer of negative pi over 16. So therefore, the potential, we can just stop here in the expansion. No need to go to the octupole term, because in this case the quadrupole is the dominant term. So the potential here at large R will be just this potential here. So you multiply all of this, and all of these values of the integral, divide by r cubed, and multiply by 1 over 4 pi epsilon naught, and you get this result. But take note, that's not actually the problem. The problem that we are trying to find the potential for points on the z-axis. So for points on the z-axis, take note, our r here is the three-dimensional position vector, is square root of x squared plus y squared plus z squared. So at points on the x-axis, the z-axis, the value of x and y coordinates are actually 0, meaning r will approach to z, or r just equal to z at points on the z-axis. So at points on the z-axis, so this is actually the coordinates of those points, 0, 0, z. So the potential only depends on z. So you just replace r by z, and this is now the potential for points on the z-axis far from this sphere with varying charge density. Okay, let's now focus on the electric dipole. So because we will most of the time we will be encountering more of the electric dipole than the monopole or the quadrupole terms. So this is what we call a physical dipole, a pair of positive and negative charges with the same magnitude q. Now, the dipole moment is actually, this is the electric field pattern. You will notice that the electric field pattern the electric field lines comes from the positive charge and it points towards the negative charge. So the dipole moment is actually opposite in direction with the electric field in this region. So the dipole moment is always from the negative charge directed towards the positive charge. That's the dipole moment. Now, at large distances, when your field point or the location of where you want to try to find the potential is very large as compared to the distance between the two charges, then your physical dipole will approach that of a pure dipole. A pure dipole is sometimes also called a point dipole because it has no dimensions. It's similar to a point charge. A point charge, if you draw a point charge on a point dipole, they're just points. They're just the same. They're just the same. But instead, it's a dipole. So if you have a pure dipole or a point dipole, it no longer has a distance. A distance you can no longer see the positive or negative charges, and instead you will see just a single point, and the electric field lines will now look like this. So you will actually, this is actually what the field of a physical dipole looks like when viewed from a very, very far distance. So this is what the field of a physical dipole will look like when viewed from a very far distance. Take note that even though this is a composition of 2 point charges, but if you look at this, if you look 2 points from a very far distance, it will actually anything, even if it's 3 points or 4 points or 5 points, or even if it's a quadrupole, or even it's an octupole. If you look at a very far distance, it will just look like one single point. So eventually, quadrupoles and octupoles at large distances becomes a pure quadrupole or a pure octupole, or they become point quadrupoles or point octupoles. Now, going back to the dipole term in the monopole expansion, so I think we have discussed earlier that if you have r cosine theta, that's actually just a dot product of your vector r prime in this case with the unit vector r hat. So again, dot product is commutative. R prime dot r hat is just equal to r hat dot r prime. So if we utilize that, if we replace r prime cosine theta here by r dot r prime, so r is no longer it's not a prime coordinate, so we can take this out of the integral. So what's left of the integral will be this term. This will be what's left of the integral, and that is actually our dipole moment, that with r. So actually we have achieved this result earlier. This is actually just p cosine. This is actually just p cosine theta, or qd cosine theta, if you have a physical dipole. So in general, if you have a pure dipole, its dipole moment is just k p dot r over r squared, where p is this defined by this dipole moment. So take note, this is just r, and rho d tau is basically just dq. So basically this is just r times q. So if your r is d, and if your dq or integral dq is q, so you have qd, the dipole moment of a physical dipole. In terms of the if you have a discrete charge distribution, so it's just r times q. So again, this is just dq, r times dq, integral of r dq, and in terms of discrete is summation of r times q. Okay. So let's have an example on how to find the electric field of a pure dipole. So this is our pure dipole. So what electric field function will describe this electric field pattern? So we start with the potential of the dipole. So p dot r hat, again, we can write that as p cosine theta, the magnitude of the first vector p, the magnitude of the second vector. Since this is a unit vector, its magnitude is 1. Then cosine of the angle between them is cosine theta. So we then utilize our formula for electric field, that is, it is just the negative gradient of your potential. So in spherical coordinates, this is what this gradient looks like. So the first term is actually just the r component of the electric field. The second term is the theta component of the electric field, and the last term is the phi component of the electric field. But you will notice that the potential of the dipole only depends on theta and r. So meaning it has no dependence on the azimuthal angle phi. So it will not have a phi component. So for the r component, it's just negative partial derivative of the potential with respect to r. So if you get the partial derivative of this with respect to r, you will get this result. For the theta component, it's just negative 1 over r, the derivative of the potential of the dipole with respect to theta. So cosine theta is obviously negative sine theta. There's a negative sign, so you will get this result. So therefore, the electric field of a dipole in spherical coordinates is just this one, r hat, plus this one, theta hat. And we have this equation. Okay, we can actually convert this equation into a coordinate free form, free from any coordinate system. So to do that, we need to define our dipole moment P first. So we will assume that it will only have an r component and a theta component. So PR r hat plus p theta theta hat. And again, as what we have discussed earlier, I don't know if I still have those slides. Oh, I already erased it. But to get the r component, you dot the vector with the r hat vector. And to get the theta component, p theta, you dot the vector p with the theta hat unit vector. So that's it. So p dot r is actually just p cosine theta. So okay. So if this is our vector p here, and we are trying to find its component, its r component and its theta component, then this is the PR, and this is the p theta. So this is our angle theta here. So PR is obviously p cosine theta. And how about p theta? P theta is what? So if you dot the p vector and the theta hat vector, So you get the magnitude. So P dot theta hat, according to the law of dot product, magnitude of P, magnitude of theta hat, which is just 1, cosine the angle between them. So what's the angle between P and the theta axis? So this angle, the angle between them, this is actually pi over 2 minus theta. So cosine, so you have cosine pi over 2 minus theta. And what's cosine pi over 2 minus theta? That's actually just negative sine theta. So you will have P, negative P sine theta. So P dot theta hat will be equal to negative P sine theta. So that's P dot theta hat. Okay, so we can now transform this electric field. So P, if we place P inside this term here, so we'll have 2P cosine theta and 2P sine theta, and that 2P cosine theta r hat plus 2 plus P sine theta theta hat will just be equal to this one. So since P cosine theta is just P dot r hat, and P sine theta is negative P dot theta hat, so that one. Now, note that our dipole P can actually be written, or this, this term here, P dot theta hat, can actually be written, P dot theta hat can actually be written as P, our vector, minus this one. You transpose this in the other side of the equation, so you have P dot r hat. So we can actually write this P dot theta hat as P minus P dot r hat, so that our terms will be in terms of P dot r hat. So doing so will give us this equation. So we replace this P and this term here with this term here, 3P dot r hat minus P, and this is now the electric field of a dipole in coordinate freeing up form. So take note, P here, the P vector here can be in any coordinates, Cartesian, cylindrical, or spherical. The r hat here can be in any cylindrical, in any coordinate system. It can be in Cartesian, so it's in terms of x, y, and z, or it can be in cylindrical in terms of s, phi, and z, or it can be in cylindrical, in spherical, which is just r. R is just r in cylindrical coordinates. So this is the electric field of a dipole in coordinate free form. Okay, so that's it for this chapter. So I hope you have learned some techniques in evaluating the potential. So if we so let's enumerate first. To summarize this chapter, we have the method of images, then we have the separation of variables in Cartesian, spherical coordinates, and of course in cylindrical coordinates, and then you lastly have the multipole expansion. So those are the three main techniques in finding the potential. Again, why are we finding the potential? It's because it's one of the easiest to find. So if you know the potential, you can solve for the electric field and you can solve for the volume charge density rho. Okay, so for our next chapter, it will now be all about the interaction of an electrostatic field with matter. So that's actually a very long chapter, so I will see you hopefully again in the next chapter. So please hang on. So that's it for this chapter, and I will see you again in the next chapter.